created by applied cybersecurity student Bleddyn. Please enjoy.
Parents have to have it easier to make with this free
Women to give up their soap.
You want it ASAP.
Potato chip. Now some people
boldly go where no.
Hello travelers. Welcome to the mainframe. My name is Bit. And today we will be learning about the differences between the TCP/IP and OSI protocol models, and we may even have some fun along the way. Let's go. So what are these models? And what do they do? Think of them as two great big theoretical networking flavored cake. On the left we have the Open System Interconnection, or OSI cake. It's got 7 distinct layers and tastes faintly of vanilla. Or so I've been told. And on the right we have the Transmission Control Protocol/Internet Protocol cake. It has been on the shelf for a little bit longer, and it has only 4 layers. But hey, it's still cake, so it's still good and tastes of cinnamon. If these flavors don't sound good, then that's okay, because as far as you're concerned the cakes are a lie. Now let's take a closer look at them, and a look at some of those gooey layers in a bit more detail. Starting with OSI. Developed in 1984 by the International Organization for Standardization, or ISO for short, the main goal for this standard was to define the different stages your information and data have to go through in order to travel across a network from one device to another. As you can all see. Yes, even you in the back. With the silly haircut, we have the 7 layers that make up the OSI reference model, starting with number 7. Application. Number 6. Presentation. Number 5. Session. Number 4. Transport. Number 3. Network. Number 2. Data link. And finally my favorite, number 1. Physical. These are the ingredients to our cake, and they can help you conceptualize how the different parts that make communication across a network possible work, how they divide their tasks among one another, and how they relay information to each other. Now before we can transport the data, we have to make the cake, starting with layer 7. Application. As you may have guessed, this is the layer that interacts with the application or operating system whenever a user on the network wishes to perform a task requiring data transfer. Such as sending that awkward email they've been putting off for the longest time. Sorry Susan in HR, it's not me, it's you. Additionally, this is the layer where protocols are defined for the information that is being sent, such as in this Office faux pas example, Internet Message Access Protocol, IMAP, or Post Office Protocol, POP. So now that our user has pressed the send button on that email and consequently immediately regretted their decision, it passes on to our next layer, number 6. Presentation. Here we take the data provided by our previous layer and translate that into a standard format that can be understood further down the line. It is also at this layer that data compression and data encryption take place. For example, when you make a video call, the data will be compressed at this stage to allow that information to be sent faster across the network. It's easier to move a body that you've broken down into smaller pieces after all. Once the email has been translated and compressed and encrypted as necessary, it's on to layer 5. Session. Now unfortunately, this is not the type of session you go on with your friends and a few too many beers. However, it is still definitely necessary to make sure our user's email gets to its intended address. It's at the session layer that connections between computers are established, controlled, maintained, and then ultimately terminated. They'll be back. On top of that, it is at this layer that data is verified, authorized, and authenticated. Now, it's here that things really get going as we move on to the transport layer, layer 4. It is within this layer that the flow control of data between point A and point B is controlled, ensuring a consistent steady stream of data that the receiving device can understand is sent without overloading it with more information than it can handle. Susan in HR is running Vista after all. Joking aside, if a steady stream of controlled data is not provided, this can lead to the information not arriving to the other user due to the recipient computer not being able to process it fast enough. Once the flow of data has been handled, we then find ourselves in layer 3, the network layer. This layer handles things like the way that data will be sent to the end device using logical protocols such as IPv4 and IPv6, routing, and addressing. Creating a roadmap for messages spreading from node to node within a network, potentially splitting this into several pieces and spreading it across the network to be reassembled at the other end, dependent on the size of the message. So, our data has the roadmap, it's stocked up on snacks and has a playlist put together. It's now onto layer 2. The data link layer, from which the transfer from node to node is handled. The appropriate physical protocol is assigned. For example, IEEE 802.11, or as it's normally known, Wi-Fi. The data link layer is often divided into two sublayers, media access controlled, or MAC, and logical link controlled, or LLC. The MAC layer is in charge of controlling how devices contained within the network gain access to information and provides permission to transmit data, whilst the LLC layer is responsible for the identification and encapsulation of network layer protocols, as well as other roles such as error checking. Now, as Olivia Newton-John once said, let's get physical, as it's onto the final layer. This is the layer where the actual hardware is contained, and it helps to define the physical configurations of the network, such as voltage levels. For example, this is the layer that would control the frequency for wireless devices connected to the network. It is within the physical layer we control the transmission of data in its physical form. Once data has reached this point within the network and reached its destination physically, the data makes its way back up the model until it is received all the way into Susan's inbox. This process of heading down the model and then back up the other side to its intended address is known respectively as encapsulation and de-encapsulation. But we'll touch more on that later, as we have more cake to see as we move on to the TCP/IP protocol model. The TCP/IP model was developed in the 1970s by the United States Department of Defense with the aim of specifying how computers transfer data to each other. The model is named after two important protocols contained within it. Firstly, the Transmission Control Protocol, or TCP. This defines how different applications and programs can create channels across a network to communicate with each other. It also manages the process of disassembling and then reassembling a message into smaller packets before and after transmission. Then we have IP, or Internet Protocol, which defines how to address and route packets of data to ensure it reaches the right address, with multiple checks along the way. As we mentioned at the start of the video, the TCP/IP model only has 4 layers, which are broken down as follows. Layer 4. Application. Layer 3. Transport. Layer 2. Internet. And Layer 1. Network access. The TCP/IP model combines multiple layers of the OSI model together, such as Layer 4, which combines the application, presentation, and session layers of the OSI model, as well as Layer 1, which combines the physical and data link layers. The main reason for this is mainly due to the two models being developed apart from each other and striving to achieve different things. TCP/IP is a protocol-centric model, with the protocols being developed first and the model then being centered around them. TCP/IP helps with establishing a connection between different types of computers and is used all over the World Wide Web to this day. Whereas OSI is a more conceptual and generic model, focusing on the functionalities of each layer, using these layers to help standardize compatibility between modern hardware and software. So let's take a closer look at the layers of the TCP/IP model, starting with Layer 4. Application. The application layer is the group of applications that require network communication, like your email client or internet browser. This is what you, the user, generally interacts with and contains protocols such as HTTP, FTP, POP, and IMAP. It combines layers 7 to 5 of the OSI model into one. Applications in most cases will perform all of the steps contained within this layer, such as taking the data you have requested to send and preparing it ready to move on to Layer 3. The transport layer. It's within this layer, as with the OSI model, that a reliable data connection is created between two devices. The data is divided into packets, and once they have been dispatched, this layer waits until it has received acknowledgement of them reaching the other side successfully. It's here that protocols such as TCP and UDP are used. Next we find Layer 2, the Internet layer, which is also known as the network layer. It's at this layer that the packets we have just created are dealt with and moved around from device to device, often using connections from independent networks to help move these packets across network boundaries. It's here that IP and ICMP are used. If you've ever heard the term ping, then you've used ICMP, which is used mainly for error reporting. The higher the ping, the less likely you'll manage that quad in Quake. Then finally we end up at layer 1, network access, or as it's also known as, the physical layer. Nice. It's here we combine the physical and data link levels of the OSI model, and we find protocols that operate and deal with the physical components of sending and receiving data, using things like Wi-Fi, Ethernet cables, and interface cards. So there you have the layers of both models. But how does data travel across them? For that we turn to encapsulation and de-encapsulation. So do you remember our user and Susan in HR? Let's use this poorly worded and probably inappropriate email as an example. Once our user has pressed the send button, the email is taken by the application layer, or layers if we're referring to OSI, and turned into a data stream. Here the layers can add what is called a header or a trailer to the data stream. This is protocol information that is added before the data, a header, or after the data, a trailer, and is specific to each protocol. This email data stream is then passed onto the transport layer, where it is broken down into smaller, more bite-sized chunks. Once this email has been successfully broken down, a header is added to each piece of the email, containing all the information, to help put it back together at the other end. Like assembly instructions for your flat-packed generic Swedish brand furniture. With the addition of this header, this piece of data is now called a segment and is handed down onto the network or internet layer. The network layer creates an additional header for each segment of the email received from the transport layer. This header contains all the information needed for the addressing and routing of this data, such as the origin and destination address. Once this new header has been attached, this segment evolves into what is called a packet. This packet is then handed onto either the data link layer in the OSI model or the network access layer in the TCP/IP model. Once this layer receives the packet successfully, we have a header and a trailer added to each one. The header contains information required for switching, such as addresses, and the trailer contains important information that helps on the other side with the detection of corrupt packages. Once the packet has this information added to the front and back of it, it is now referred to as a frame and is then passed onto the physical layer. However, if we are using the TCP/IP model, the next step still takes place in the network access layer, which contains both the data link and physical layers of the OSI model. Once the frames that make up our ill-fated email have been received, these are then converted into a format known as bits. This is a series of ones and zeros that can be used by the relevant hardware. So if the data is being transmitted over copper wire, this is received as voltage. Or if we're going newfangled and wireless, this will be in the form of radio signals. This will help our data actually traverse the network all the way to our end destination, Susan's computer. This process is called encapsulation. Once the email has flown across the network from node to node and been received at its end address, the process resumes again, but backwards, all the way up the other side of the model. So the physical layer, or the network access layer in the case of TCP/IP, picks up the bits of information and converts them to frames and hands them to the data link layer. The data link layer then reads the trailer of the frame to make sure that the information is not corrupt. If the frame is corrupt, it is discarded and no further action is taken. However, if everything is in order with the trailer, the rest of the frame is read and its header and trailer are removed to make it a packet again. This packet is then handed to the network or internet layer, where the software destination address is read and the packet header is removed, making this a segment again, where it is then handed over to the transport layer. It is in the transport layer that the headers of all the segments are read and all the necessary information is collected to piece them back together again in the right order at the target destination. Once the segments have been put into the correct order, the segment headers are removed. It is reassembled into the original data stream, and it is then handed over to the upper layers, where it is converted into a format that the target application can understand. Such as with this example, the email client of Susan in HR. This process of reassembling the data from bit to data stream is called de-encapsulation. So now that we understand what makes these two models tick and how data travels across them, what are the main differences? Whilst both models are conceptual models used to describe network communication, OSI is more of a conceptual model, which is generally not used for communication. It is instead used to help define how and why applications can communicate successfully over a network. However, on the other end, TCP/IP is regularly used to help establish links between networks and to help them interact. The protocol helped to lay the groundwork for standards on which the World Wide Web as we know it today was created. So in summary, TCP/IP is a model for client-server communications and is a standard used for networks the world over, including the Internet. And OSI is a conceptual model and a reference model useful in helping to understand and design system architecture. We have now reached the end of our presentation. Any questions? That's great, however my name's not Dora and I can't hear you. Thank you travelers for visiting the mainframe. Please keep your arms and legs inside the data stream at all times as you leave. Good night.